In previous lecture, good morning all of you. In previous lecture, we discussed about the basics of the vibrations. So in that basics of vibration, and we also go through that equation of motion for a particular system. So while defining that equation of motion for a particular system, we consider two parameters which are essential for vibrations are the mass and the stiffness, M and K. So these two parameters are essential for vibration in the system. If one of it, that parameter is absent, then there is no possibility of vibration. But these two parameters are always exist in any system. So in that system or in that equation of motion, we consider two parameters, mass and stiffness, M and K. Here in this equation, or while solving this equation of motion, we consider that there is a no damping. There is a no damping, or damping is absent. What is it means damping? Damping is nothing but a resistance offered by a substance, by a certain or by a substance to that vibratory motion. So resistance offered by any mean to the oscillatory motion of that particular body is nothing but a damping. So damping is nothing but we provide some external or internal resistance to that oscillatory motion of that particular body. So damping is nothing but resistance. Now we introduce another parameter in combination with mass and stiffness or M and K. We introduce one more parameter as a damping is denoted by coefficient of damping C, is denoted by coefficient of damping C. So one more parameter we introduce as a C. Now here this damping is generally essential to control that amplitude of particular vibratory system. Control amplitude of particular vibratory system in a resonance condition. So it is essential to control that amplitude of particular vibratory body in resonance condition. So in that case we use damping. Damping provides a significant role in controlling that amplitude in resonance condition. So we go through that how that damping control that amplitude in resonance condition in detail in the post vibration topic. So here we go through this damping types, or what is meant by damping. So damping generally, this damping is this 4 type here mentioned. One more is the here fifth type is mentioned as a eddy current damping. So in these types of damping, 4 major dampings are introduced here: viscous damping, Coulomb damping, structural damping, slip damping, and one more is the eddy current damping. So generally viscous damping and Coulomb damping are major contribution in terms of external damping. So structural damping and slip dampings are this contribution is a small one. Structural damping and slip damping contribution is a small one. Major we can find out in a practical application, viscous damping and Coulomb damping. So we just move further towards the viscous damping. So here damping nothing but resistance provided to oscillatory motion of that particular body. Now as viscous damping, it means that resistance offered to the motion of system by viscous medium. That viscous medium in terms of oil or any another material, any another viscoelastic material. So this damping is called as a viscous damping. Generally in practical application we observed a viscous damping is provided or external resistance given to that particular vibrating system by means of viscous damping. So here we consider two plates. One plate is fixed one. Here two plates are shown here. One plate is a lower plate is fixed one and upper plate is moving. Upper plate is moving with some velocity v. With some velocity v. And these both plates are separated out by a thickness t or by space t, and this space is filled with oil. This space is filled with oil. One plate, lower plate is fixed one, above plate is moving with certain velocity v. Now in equation of motion, while deriving equation of motion, we consider that velocity is denoted by x dot, acceleration denoted by x double dot. So velocity is nothing but derivation of the displacement d by dt of x, which is denoted by x dot. So velocity here we denoted by x dot and acceleration we denoted by x double dot. X double dot. So here v is equal to x dot. So velocity we denoted as x dot. So here one plate is moving with respect to this fixed plate, separated out by some distance t, which is filled by a viscous oil, having coefficient of here this coefficient of viscosity mu, and A is the area of plate which is contact with that oil. A is the area of the plate which is in contact with that oil. So here A, T and mu, that are related to the oil, or these quantity are contact with that oil. So A is the area of the plate, which is in contact with that oil. So that force, now how much force is required for this upper plate to move with certain velocity v? Separated out by this viscous fluid. This force is nothing but a c into x dot. Here c is equal to mu a by t. This damping coefficient c is equal to the mu a by t. So it is proportional to the mu a and inversely proportional to the thickness of that fluid film. So mu a by t is nothing but a c. And that damping force in that viscous medium is F is equal to c into x dot. Where this c is nothing but a damping coefficient. So this c we introduced in equation of motion. Further. So again this damping is provided by means of damper. And that damper arrangement is like this. So one cylinder is present. In that cylinder, one piston is provided with piston rod. Attached with piston rod, and that piston is moving inside the cylinder. And that piston and internal diameter of that cylinder having some gap in between this piston and that internal diameter of that particular cylinder. So while moving this piston in the downward direction, oil from this bottom side is passed through this clearance provided between this piston and this internal diameter of that cylinder. So this oil is passed through this gap between this piston and the cylinder, and then this oil is moved on the upward side and the piston move on the downward side. So that internal resistance offered by that oil to the surface, which is to the surface of this piston, that oil and this piston area come into contact, and there is some viscous friction. Occur to this piston area, and that is nothing but that resistance we can call as a viscous damping. That resistance we can consider here as a viscous damping, and that depend on the C is equal to mu a by t. is equal to mu A by T. So in viscous damper, this viscous damper we generally observe in automobiles, and generally we observe in automobiles to absorb shocks, that were offered by that road surface, while vehicle in moving condition. So this viscous damper is nothing but a cylinder piston arrangement having that piston and internal diameter of that particular cylinder having some clearance, and that resistance, or that oil provide some resistance or due to the friction in between the surface of that piston come into contact with that oil, and that is nothing but a viscous damping. So this viscous damper we generally observe, this principle of that viscous damper is generally observed in day-to-day life applications. So this is called as a viscous damper. So this viscous damper provide a resistance offered by that particular viscous medium, Now by introducing that C term, so previously that equation of motion is nothing but only considering M and K. So that equation of motion previously it is a mx double dot plus kx is equal to 0. Now here one more term we introduced here as a plus cx dot. So while deriving that equation of motion, we consider this kx is nothing but a spring force, and which is opposed to the motion, which is opposed to the accelerating force, mx double dot. Similarly, to this accelerating force, this damping force is also opposite. So in that derivation of that equation of motion, mx double dot is equal to minus kx and minus cx. So that minus kx and minus cx come on this left side, and this equation we will obtain as a mx double dot plus cx dot plus kx is equal to 0. So this is nothing but an equation of motion by considering viscous damping. If this C term is absent, it means there is no resistance to the oscillatory motion of that particular body, or very negligible resistance offered to that vibrator motion of the body. Suppose that simple pendulum is oscillating in air. So air has a very small or negligible damping resistance to that motion of that particular pendulum. In that case, we consider that C is equal to 0, and that equation now becomes as a mx double dot plus like that. So very negligible amount of damping we can consider as a C is equal to 0. Now we consider as another damping as a Coulomb damping. This damping is also called as a frictional damping. So this damping offered due to the friction between the two surfaces. Suppose this lower surface is fixed one, and this body is moving along the surface, and there is some resistance to the movement of the body due to the friction observed between the two contacting surfaces of this body and that fixed surface. Now that frictional force is equal to mu Rn. Now here mu is the coefficient of friction. And Rn is the normal reaction. Which is exactly opposite to the weight. So when this block is moving on the fixed surface with velocity x dot, a frictional force in opposite direction is applied is equal to having value mu Rn. Rn is the normal reaction, mu is the coefficient of friction. So this resistance offered to the movement of this particular block, or oscillation of this block, is due to the friction in between these two contacting surfaces. This is nothing called as a Coulomb damping or frictional damping. Another one is the structural damping. So in structural damping, this resistance offered due to the intermolecular friction